light blinks.
Does it?
Yeah, it's okay.
Ah, it does, you're right. Okay, today we will review very shortly the time binding approximation, which you've already learned, understood, did the homework. And so what is the idea of time binding approximation? We
approximate the crystal states with the atomic orbitals, a linear combination.
We use them as the basis. So this is the origin of the linear combination of atomic orbitals method in chemistry that we use, which is the same as time binding. So we will express, you don't have to write any of this review, it's what you have in the notes. I'm just trying to make sure that we are all on the same. We can write our state as the sum of all the coefficients, of the block states what is, you use the same indices I checked. So what is the index mu standing for? The mu is for
it's the, as far as I remember, index of atom in the unit cell.
In the basis.
Yeah, in the basis.
So if you have more than one atom in the basis, you have mu 1, 2, 3, whatever. And I is the index of the state.
Yeah.
So you have px, 2px, 2py, and so on. This, I know that you proved it's a block state. And this can be written because what you have potential on the atomic sides with different states now, 1s, 2s, and so on. These states are my basis. So using this state at every lattice point, I automatically create something periodic. So if I had just the sum over all the R of the atomic functions, am I missing something? Okay, I would have something periodic, but not the block functions. So I need E on the KR to make sure I have the block theorem satisfied. But only this sum is something periodic. That was in the exam and many people didn't answer it right. Okay, this is my basis. And I have a Hamiltonian, which I'm solving, which I can write plus. So now I can take just potential at the one side. Potential is the sum of all the potentials, atomic potentials at all R. So I will take just at one side and then subtract from the total this potential I took. Total minus the atomic at R 0, let's call it. And this is my atomic potential. Actually, it should be plus 0, let's call it, at 0, at R equals 0. What is the meaning of this potential?
The Coulomb potential.
It is just this.
Yeah.
No, just this. What is the meaning of this potential?
The crystal
potential from the whole lattice of this atom.
So, it depends on what?
On the lattice.
On the symmetry, on the lattice. So it gives you exactly the effect of how the atoms are arranged in the crystal. Good. And I will get the terms now. I won't write the second equation, but you will get the terms dependent only on the atomic part and only on this crystal field part. And you can differentiate when you solve them at the same R, or you can choose R0 at this same R, or different R. Are you familiar with the concept? When you evaluate the terms, you can see it's becoming longer. This is a short review. So what you will have here, what kind of term? You will write the whole function. This one times atomic times this one at some different R. So if the R is the same, it's easy to evaluate. That gives you the atomic energy. Energy atomic. However, if you have a situation that you have something of this type, what is this?
The overlap.
Overlap term. And this is a situation where you have two sides. Okay, maybe better I show it just like this. You're actually looking for this overlap. And we take this usually to be 0. So this is not orthogonality, as people wrote in the last exam. It is simply that it's very, very small, this overlap. So I'm setting it to 0. Doesn't have to be set to 0, it's just for simplicity of our calculations. But actually, it is these overlaps in these terms with the V prime which make you get a new physics from the atomic. Are you following?
Yeah.
Okay, and then we have the second term. Then we have the second term with V prime. Good. And here you have a term at the same R. Okay, maybe I can do it for just a single band. No? In the case of single band, I think you've solved it. Then what do you get? Energy is equal to atomic of that single band minus or plus, we'll see later, plus the term which comes from V prime, which is at the same R. So assuming the same R on both sides. And do you know what is the meaning of this term? So it's on-site term. The first, yeah, within this V prime, what can be all called hopping, although it's not very precise. The first term when you have the same R at the same atom.
If it's on the same R, then it's not hopping.
It's not hopping. You will get a sum here of two terms.
Yeah.
The same R and real hopping term. It's all called T in the notes,
Yeah.
I know. So roughly it is originating from the same type of matrix element, just with the same R. This is the crystal field potential. So this is the effect of the neighbors making an offset term. So this is what we given a value, delta V, delta energy, whatever. And this is positive or negative. Will this lower the energy in total or make it higher, this term?
It is negative.
It's lowering the energy. Why? A simple argument thinking. It's the interaction due to first neighbors. It makes it more stable because the crystal is bound, no? The crystal is stable, otherwise it wouldn't be a crystal. It would just and this has to make it more stable, otherwise it cannot exist. So you can write it this delta V positive with a minus here, or keeping it in mind it's negative if you write plus. And then you have the real hopping term, which can be written as the sum well, you can have two R's here.
Sorry, can we restate the thing about the sign of delta V?
Yes?
Like, the way we wrote it down, is it defined as I don't
P
really understand
positive.
why
P
delta...
positive. The whole thing should be lowering the energy.
Yeah.
This is what you know physically, no? I can write this as minus, and then this is positive. Keeping it positive defined. This was a short overview, review. Any questions on this? We'll go to graphene, to the example of graphene, and do it in detail. But before, I will finish something that I couldn't finish last time. That is a case of two p orbitals in a square lattice. So I think it is an example of a single orbital, no? Which becomes trivial after a while, no? You'll be saying, oh, that's too trivial. So what do you have? A square lattice. And two p orbitals, px, py, we are in 2D. You probably know that atomic orbitals have a phase that can be noted as plus and minus. This is the atom 0, let's call it. Atom 1, 2, 3, and 4. I will not write the whole thing, I will just go for this part of the system. No, this is trivial atomic part, to make it short, just the T part of the second equation. So px and py. 0 can interact with 1 in two ways. It can be the px orbital with the px orbital of the neighbors in the x direction. So I can write px at the site I as ix. Okay, but it's not so important how do I write it. Yeah, better like this. So I will have they are interacting along the axis of the orbital. I'm not sure how much chemistry you learned. There is something called sigma and pi bond. You've heard of that. So, if they are binding along the axis of the orbital, it's called sigma bond. However, we have here a bit of a bad situation because the phases are opposite. For them, you came for them to create a bond, they should have the same phase in the center. They should have something of this type, plus, plus. And then they create some kind of however, this is still called a sigma bond. And this overlap we will denote as T sigma. And this is what you want to have. This is the binding type. This is anti-bonding. This is bonding and anti-bonding. So this T sigma will be larger than 0 if you have Coulomb interaction in between. But then, in this direction, if I have interaction of px with px, I have a different situation. I will have my zeros, and then the one above, plus, plus. These guys can interact and lower their energy. They will create electron cloud in between. They will just get a bit wider. And this is called pi bond. In this case, it's lowering the energy. So let's write all the possibilities, what we have in this case. Yes,
Assume 1, 2, 3, 4, these are 1s, 2s.
No, sorry, just the atoms, just the neighbors. Because time binding comes essentially to counting neighbors.
Okay.
So I just put the numbers that it's easier to refer to them when I'm writing. It's nothing.
And the state we're looking at is just 2p. We don't look at other states.
Just the x, dy.
Okay.
That's all we are looking at. Okay, so let's write the t, px, px pi. First we have an on-site term at the same site, so 0 with 0, which I can denote as, how I call it, 0, yeah? 0x, v prime, 0x. Okay, and then I have the neighbors. This is a square lattice. Distance between the neighbors is a in all directions, okay? So I have a term, AKR, sum, and then the overlap on, then the matrix elements of the two. O, 0x, v prime, and then Rj, the first neighbors, Jx. This is now what I will write down completely. This is a generic form for everyone. Okay, and the J goes over 4. There are 4 first neighbors. If you want to improve results, you can go to second neighbors, but we'll keep, only first neighbors always. So, the first neighbor is along x at the distance a. So it is kxa, 0x, v prime, and it is a sigma bond. So, but okay, it will still the x orbital which is interacting. The second one is the minus x. It's called 3, no? Yes. Good. And now along y, we have 2 neighbors. And we said this term, this matrix element, we'll call sigma, T sigma. T sigma, T sigma, and this is T pi. Okay. This is the crystal field, minus delta V. Plus T sigma, I have IKXA minus IKXA, which is 2 times cosine KXA, and very similar for the pi. Everyone understood everything here? Okay. So what happens? This is the PX case. Okay, what in the case of TPX PY? I will have to remove this. So will be the first term with the first neighbor. So this x with this y. So I get first it will be well, X and Y cannot interact. It will give 0. I mean, can give 0, so 0x, 3 prime, and 1y plus, there is an ikxa plus I minus kxa, 0x, 3 prime, 3y,
Why doesn't have interaction with itself? Because there we had interaction.
It does, if you remember the how did you call it? I think you call it like this. It was, you put it like minus delta V. This was the definition that you put. So here, what do I have? This X interacting with this Y. In principle, they could form a bond here, something along this direction, something. But then, what happens in this case? You create a bond here. And this essentially is not conserving the symmetry. You will create a cloud in this case. In this case, you have a next neighbor in this direction. You create a cloud here, the bonding in the other direction. You have to, everything, whatever happens in the crystal has to preserve the symmetry, the original symmetry of the crystal, which is a square lattice, which has reflection symmetries. Reflection along X, along Y. Here it becomes anti-symmetry for the reflection in this direction. So the only way this keeps the symmetry is if this is 0. And the same for this guy. You have this X and this. So again it will interact minus and it will create cloud here, and the bottom one will create here. The bond, the bonding. So this cannot keep the symmetry. The crystal has to be 0. Okay, so this is the TPX part. Then you can have also TPY, PY, and TPY, PX, which is also 0. This one is like this. It will just have a different indices for the pi and p bond. It will have pi bonds along X and sigma bonds along Y. So let me just save time. I won't finish the whole writing, but I think you understood the case of the two orbitals, no? Any questions? Very serious. Okay. And now we will start, we will do an example, a bit more advanced, but still quite easy, of graphene. What do you know of graphene?
Question.
Yes.
What are we going to do to the T sigma bonds? Because we said earlier that it will not lower the energy.
Yes, yes. So these ones will be lowering the energy.
Yeah.
If it wasn't for these guys, you wouldn't have the system survive.
So basically the T pi bonds are neutralizing the T sigma bonds.
It means that the bonding here is so strong that it can take not bonding in the other direction, in the other case. It's the basic stability. you compare the system, the energy of the bound and of the separate, and whichever is larger, that's going to, smaller is going to, lower is going to survive. So graphene. Oy.
One more question. If we write the total dispersion relation,
Yes.
it will have like cosine times T sigma plus T pi, and then another cosine with the same coefficient in front.
This will change. This is for
Yeah.
TXPS.
For the other case
it will be pi, T
it will
pi.
be switched.
Yeah.
So the total dispersion will have cosine kxa times T sigma plus T pi.
Yes, yes.
So the symmetry is still conserved.
Yes, exactly, exactly. It takes time. We already like 36 minutes into the lecture, and I was hoping to also do the FCC problem, but let's see. Okay, so graphene. What do you know? You know something. It's a 2D. Don't be shy. Don't be shy.
It's a 2D
Sheet of carbon atoms, and the properties. It's extremely.
Two atoms in unit cell,
Okay. Yes.
so not a brave.
Yes. It is. What lattice is it? You know. I'll draw it.
A honeycomb.
Honeycomb lattice. Or triangular with two atoms in the basis. And the properties of graphene, it is extremely strong, hard. I think it goes like it's 100 times harder than steel, than the strongest steel. And I mean, in this, they got a Nobel Prize for producing it, no, many years ago. And in the justification of the Nobel Committee, in the document, the official document, they were saying that it's so strong, and they draw a picture of a cat in a hammock in the Nobel Prize justification, saying that on 1 meter square of graphene, you can make a hammock and let an average cat lay on it. It won't break. I mean, and it's thin. It's 1 atomic layer thin. So its density is, I forgot how many thousand times smaller than the steel's density, and yet it's harder. It's more difficult to break. It's also a great conductor. Being a great conductor, as it commonly happens, it's also a good thermal conductor. But okay, let me not diverse too much. So it's very, very strong. Why is it strong? We can answer. It's all in the bonding. In its
Is
structure.
it because T pi bond?
Yes, we will come to the bonds. Actually, it's something called sp2 bonds. Carbon, this is terrible. Carbon has 6 electrons. Now you know that 6 electrons. So 1s2, 2s2, 2p2. And you can draw it. This is what I learned in my chemistry class. I'm not sure you're still learning it that way. No? 1s2 is the lowest energy. It should be actually the other way. And 2s2 and 2p2. And what happens in many of the systems of carbon? There is diamond, which is in 3D. And there is graphite, which is also 3D, but mostly in planes, with a very, very big bonding between the planes. What happens in this case? If one of these S2, this is 1, this is 2, if one of these 2 s electrons gets excited into P, so okay, they're all the same energy. What will happen? It will form a 3 sp2 bonds and 1 p. This is orbitals. He creates a special type of orbital, which is produced by hybridization of S and P. I'm not sure how aware you all these names. And 1p. So if you have a honeycomb lattice, let me just try to sketch it. Has 3 neighbors. So this is like in plane, looking up a bit above. This is the honeycomb now. At one of these sides, it has 3 neighbors, which I try to draw here. And they create these 3 bonds, which is Oh my God. And this is something extremely strong. This is extremely deep and extremely strong. It's hard to, this is what gives this fantastic hardness of graphene, the sp2 bond. And then there is one p orbital out of plane, which I can draw here. So this sp2, I forgot the energy, but they are very, very deep. And they're not so active. The deeper energy, the less active a level is. So what we'll do today, we'll just take this one pz orbital into account. Okay? So we are just doing the pz orbital. And we'll have two of them, because we have two atoms in the basis. So far, all clear. So our basis consists of two pz orbitals. And now the most difficult part, I'll try to draw it clearly, and I don't always manage I could start. Anyway, these are the sites where atoms are. I'm not writing anything. Let's call the two atoms in the basis as A and B.
Do we only choose PZ, correct me if I'm wrong, because since the bond between the atoms are so strong, the
sp2 are
so
really
strong.
so low in energy.
Yeah. And the only way, for example, to create graphite to layers is the interaction between.
Exactly, for everything it's interaction of PZ with something.
Okay.
Because these guys are so deep that they cannot interact. They are inactive completely.
So that's why we just choose it.
Just PZ, that's why. And I will choose my unit vectors. I can just use the same as in the notes if I have to compare. This one was A1. So this is 30 degrees, each of them. We have a cosine. Everyone agrees with this? Then I can make it more symmetric. This is my basis. So if I put the origin here, I have one atom at 0, at 1 at distance A. I can make it symmetric to have A or like 1 D and minus D. D is what you called in the notes now. So I can shift the origin to this one. I just called it differently. And now this is the new vectors. I just want to have a symmetric vectors. So A, the atom A, corresponds to D, minus D, and B to plus D. And this is then minus D and D. And what is D? So if you sum A1 and A2, you get this now. And this is 2A, and this is an A. This whole thing is 3A, do you see? So D, 2D is the 1/3 of the sum A1 plus A2. Do you follow? And 1D is then 1/6 of A1 plus A2. And it's nothing smart, I'm just trying to put a number to it. Is it okay? I'm just trying to express this distance, but I'm not going to use it really for anything. And then let me denote the neighbors. This is the 0th pair. Then this is the first pair, these two. This will be the third, not the second. Okay. So 1, 2, 3, 4. Because I'll have to count the neighbors. You have a question? And we write the Hamiltonian. Plus, I can write a sum, let me write it like this, a sum of VA of R minus R plus VB of R minus R. Because now I have two atoms in the basis. And I will call this whole thing V. So what I will write, it's always the same, no? Soon you'll be so experienced with these things, you'll be bored with writing. Actually, I can right away multiply from the... Okay, let me just write first the PZ state. I didn't write that yet. It is A R AR plus AB BR. So I have here two states. I'm writing it as a total sum of the two states. And by solving these coefficients, I'll find the eigenfunctions, the states, and then also I'll be able to find the energy levels. Maybe I can shorten. I'm just thinking now it's lots of writing. In principle, I should write this one first, multiply this times this, but maybe I can right away multiply from the left with the first part, with the AR. Is it okay? You can follow it just to reduce a bit the writing. But I won't use just any R. It works for any R. I can choose what I want to make it the simplest case. So I will choose R equals 0 to multiply from the left. So multiply this. Okay. Now we have to be careful. Please correct me. I'm likely to make a mistake at this point. So we will have A times A in the atomic part. And the term will be AA coefficient before. Atomic. They write it up or down, I don't remember. And A0. then term with A0 and R will give 0. So I'm not even writing it. We know that. So this is the term which survives from the atomic part. Because A times B will also give 0 with atomic, no? Good. And now I'll take the VI part out. So the V I can also write as VRA of 0 of R plus V minus VA of R. Not taking the R into account. R equals 0. Okay? And this is V prime. Right. So first A times A. First that part. VA. No, sorry. It was already on the atomic part here. Now it's V prime. AR. And actually, it's only for I equal 0 which survives the crystal field potential. I can write the sum if you want, but only one term survives. There is a reason why people copy from the notes. IKR AA. So this is the first term. A times this A with the V potential, V prime potential. Everyone following? This is the first part. And the second part is this A times B, first neighbors. And it won't be anymore A, it will be B. Now it's this coefficient. This is the whole thing. And this is equal energy times AA. This is the only one which survives, no?
The V prime of the VR is the one small VB, right?
This is the hopping.
Yeah, with the potential small VB.
No.
Yes, actually. There is a VA and there is a VB. You're right. You subtract the B part for you. I skip maybe too many steps, I'm afraid.
So the thing that we do, that we take the whole crystal potential,
yes.
Then we take out the VAR0 part and VBR0
yes.
part.
Depends on the site which you are.
Yeah.
I can write it if you want a step in between.
Small VB only acts at the B
At the B side,
Yeah.
exactly.
Yeah.
At the B side. So this is VB on that if you want.
Yeah.
Is it clear? I can write a step in between. Is it okay?
Yeah, I'm trying to see.
So you have potential acting at the A side, it's VA. And at the B side, it's the VB. When I take the atomic part, for each of them, I'll take VA, and then what remains will be B prime. Okay. What we have here, it's actually non-zero only for R equals 0. So this will give me minus delta V AA.
Because only we include the nearest hoppings.
But I mean, there is this delta I prime here, so it has to be on the same side to get the on-site crystal field potential. So we have the neighbors. This is the key thing up to here, the hopping. We have how many neighbors? So this side here is a neighbor number 3, number 4, and the 0th neighbor. The 0th is in the same, in the base. So let's write the 3, 0, 0. I will have just A0, V prime V, B0. Then the second one, the neighbor 3, I will have actually a phase. This is A2. A2. And this will be no, it's wrong actually. No, this was wrong. It is all VA here. Sorry. I got confused. It is all VA. I'm centered at the 0. I'll be looking from that point. Everything is VA. Sorry, I got confused. And then in the next step, when we multiply by B, we'll be taking VB. So, sorry, I got confused. It's all VA in this case. And I'm centered at the 0th one, here. I can look like that. So I can look the neighbors, the 0th of the 8th. It's a bit confusing. You go like from the A to B, but I'm multiplying from the 0th, so I'm in the 0th cell. A to, 0th one, 1 and 2. That's what I got now. 1. So number 1 is here. This is minus A1. Minus A1. And the neighbor 2. It's this vector. It is minus A2. You check that there is no surprises. Yes. Now I have here 3 integrals. Interaction between A with B. Interaction of A with B. Interaction of A with B. What was this? You can correct me, no, don't be shy. Yeah, the rest is fine. A with B, A with B, A with B. What can you tell about these 3 integrals? It is always the same. It's always the same thing. I keep rotating it, but it's the same strength of the interaction. What I have here, I just rotate by 120, I get the same one. So I get the same. And I call them T. So this part here is equal to AB times 1 plus E on the minus IK A1 plus E on the minus IK A2 times T. Is it okay? Tell me. You look very attentive.
I'm trying to understand this.
Tell me, what is the... Why is the same?
Yeah, there's the okay.
Is it coming? We just rotate. It's the same neighbors. It's coming from the crystal symmetry if you want. Okay. What do I remove?
Can I ask a question?
Yes.
The lattice, the minus A2, that yes, doesn't it link A to its to the other A?
Oh, I'm sorry. You're right. It should be from here. Sorry, but you correct me. It should be this one from the 0. This is minus. This is A2, the new one, and this is minus A2. Is it okay? I'm connecting the bases.
To B.
So A is with B.
Yeah. Okay.
A interacts with B. Those are the first neighbors. Now I will multiply with B0, and I'll be sitting at the B side. Now it will be VB potential. I got a bit confused. And I'll be looking for the neighbors around the B.
And the T's will be the same for them.
I don't know. Let's see. But yeah. I don't know what to. Also, these guys I will need. I don't know what to. So now I will use the VB potential. VB and VB. And I'll be sitting at the B side. So now I'm multiplying B0, BZ. Let me write it explicitly. So the first part, the atomic Hamiltonian, will be B with B. So this is the atomic part, no? Not right, but that's what we call the atomic. Plus, the second term will be delta V times A times B, AB. And now comes the interesting part. Let me erase this. Yeah. Let me analyze now the neighbors of the B atom. So, the neighbors of the B atom is the cell number 3, the base number 3, the base number 4, and the 0th one. So first the 0, 0, we get B0, B prime, B 0 is the same base. And then the 0, 3, that's the vector A2, which gets me there. A 3. And the 0, 4, yes, plus, it's the vector A1. Now the same story applies. This is the same interaction. B with A, B with A, B with A. So they have to be the same.
Has to
But-
be A's on the right.
Sorry, right. Yeah, B and A neighbors. The first neighbors are always B and A. And moreover, as you've already saying, it has to be the same as this T. I don't care if I call first A with B or B with A, it's the same interaction. Has to be the same amount. So this is T, TT, and this term then is equal AA times 1 plus IKA2 plus times T. Okay, so the biggest part is solved. We just have to solve this circular equation. Let me write the equations once again. The first equation says AA atomic. Also the atomic energy of A and B is the same, no? It's all carbon atoms. So it has to be the same. Minus delta V AA plus AB times 1 plus is equal. This is the first, and the second one is AB atomic minus delta V AB plus AA1 plus So we have to solve this for AA, AB, and the energy. This is what we want. So we had two states to start with, and we are getting 2 by 2 matrix determinant to solve. If you had 10 states, you will have 10 by 10. And that depends both on the number of basis states and the number of states you have. So if you took 2 orbitals into account, you will get 4 by 4. Okay. I can write it here. I can call this alpha, no? And this alpha conjugate is the same thing. So, times alpha conjugate T, here alpha T, we know how to solve this, no?
Sorry, I have this really stupid question.
No.
Why did we assume that T is real and not complex? Because it's a matrix element from like A basis vector and B basis vector with another.
This formation, I think, has to come from there.
So V
Has
is
to come from
Hermitian.
Yeah, B is submission.
Yeah. Okay,
Yeah.
let's solve this one. But there is no stupid questions. Don't be shy to ask. I think you can ask much more and then you have to work much at home. It helps you. Or it's too early for you.
No.
So what do I have here? This times this minus, well, we can write the whole thing because now I'm confused of everything. Squared minus alpha. Minus e squared 0. So let me just yeah, e will be equal e atomic minus delta v plus minus alpha t. Is it correct? And so far everything correct, I think.
Yeah.
Good. And what do I want normally? I want to draw the dispersion relation. So this is energy of K. This is what I want. I want to draw the band. For that I need to know the Brillouin zone. I cannot draw it otherwise. I have to know in which direction I'm plotting. What am I doing? So for that we need to draw the Brillouin zone and find in which direction we want to draw. Find the limits. Okay, the volume is square root of 3. I think I should just write the thing, not to take time to derive the vectors, no? This is even correct, but let me just write V1 and V2. Now you know how to get them, no? We don't have to do it 4 pi of A and half x minus draw it in the middle there. Right. This is 1 in the units of 4 pi square root of 3a, and this is the same one, the same unit here. So B1 is 1/2 x minus 1.8, somewhere here, no? This is B1. B2 is somewhere here. The sum of these two is here. And this one is way too far to be important. So I'm going to half them. Here it's 1/2. So this is roughly that. More or less. Good? And there are special points in the Brillouin zone, as you know. This one here, it's called K, and one in the center of the side, it's called M. And in principle, you want to draw the full band structure. You can draw it from gamma to M to K in between, but it's a lot of work. You can do it. But the most interesting behavior is along gamma to K. So we'll just draw gamma to K. I know that gamma is 0, 0. And what is the K? What are the coordinates of the K point? It's a long line, ky, that's good. But we have to find the coordinates. So we'll take this triangle here with the right angle to find the gamma K. So this is 30 degrees. Cosine 30 is equal 1/2 of B. This is B2 1/2 divided by gamma K. And this is equal root of 3 divided by 2 cosine 30. If I make any mistake, please correct me. It's very easy to make a mistake here. Gamma K is equal B2, the absolute value here. The absolute value is this times 1/4 plus 3/4. This gives 1. This is the absolute value. Okay? So 1/2 of this. 4 pi divided by 2, 3, 8. This is gamma K is equal B2 divided by cosine 30. Okay? So this is equal this divided by this.
2 square root of 2 over square root of
no, but I took 2. What did you say, sorry?
times 2 over square root of 3 because we're going to divide it by 2.
I'm not understanding what to say.
It should be 2 over square root of 3. That's square root of 3 of 2.
I cannot hear, I'm sorry. It should be
It's 2 over square root of 3 because we're dividing it by cosine 30.
Right. Yes, now I understand. Right. No, I couldn't understand. So what we are getting here is 4/5 over 3a. Let me check if it's correct. Yeah. That's good. Fine. And now we have to find this alpha absolute value of alpha. Because here is the function of k. This is where the dependency of k enters from. So alpha is equal. We'll just square the real part plus imaginary part. This is alpha, but with plus. Now we use plus in the definition. The real part is 1 plus cosine k a1 plus cosine k a2 square plus sine Okay, so alpha of 0 of gamma point is equal what? This is 0, this is 0, then we get 3. 3 squared, root remains 3. That was easy. What is alpha of k? So it is only ky. Now we just do ky, and we will have to remove this. me write it. 1 plus cosine ky times y part is this, minus 1/2. Are you following?
Yeah.
Plus cosine ky times 1/2 of A squared plus sine of ky minus 1/2 of A plus sine ky 1/2 of A. Right away, sine is an odd function, sine plus and sine minus is 0. And we are left with this. So we have, and this is an even function. So we are getting 1 plus cosine ky a/2 2 times. Okay. And what is the ky and the k?
4 pi over 3.
So we have 1 plus 2 times cosine of 4 pi over 3a, put that times a times 2. What's the writing now? 2 pi over 3. Okay, this is 120 degrees. Cosine of 120 is terrible. No, I never know these things. 180, 90. It's minus 1/2, no? Oh yeah, actually I should know it. I am minus 1, yes. I know what I should get. It's 0. Okay. Let's draw it. And we're almost there. So this is the energy of K. This is along ky direction, gamma and K point. So this alpha we have enters as plus and minus. So with plus and minus 3, the energy is E atomic minus delta V I minus 3T minus 3T. And plus part is E atomic minus delta V plus 3T. So this is the point at gamma, and at K it's 0. In principle, you can also find this as a function of K. Just to plot it, you can use any plotter online. You get something like this. This part here enters linearly. This is a very particular thing of graphene. And the same thing symmetrically. More or less, it should be the same thing. And now, how is it filled? We have 2 states. And we start filling from the bottom. Now, we don't have the full band structure. And what you have to do, you have to believe me, trust me that there is, all the bands are below this point, all the other parts, throughout the brilliant zone. You cannot do this without knowing the whole band structure. But all of the bands are below this point. So, in this band here, which actually expands over the whole brilliant zone, you can put 2 electrons. And that's what we have. So you will fill all these states up to here. And the Fermi energy comes exactly here. This is also, by chance, our Fermi energy. And all the rest, if I had drawn to gamma, gamma m, they're all below this. Actually, I forgot to bring the paper for that. I'll bring tomorrow, hopefully. So this is the Fermi energy. And the bands, the valence band is touching the Fermi energy at one point, at only one point. So we know it has to be a metal because it is touching it, the very end of the occupied band. But it's a weak metal, if you want, because everything else is below. So just at one point. And they made up a new name for it, calling it a semi-metal. So it is a metal, there is no gap, it's a metal, but not a good metal. And exactly this dispersion here, it's linear. And this creates the Dirac cone, which maybe you heard, a linear dispersion around the K point, which gives very particular properties, a very good conductivity. And tomorrow I will talk about that in the second part of the applications of the band structure. So this finishes graphene. Any questions?
There was something from the previous courses, previous lectures, that I remember that the derivative of the dispersion has to be zero only. Age of the Brillouin zone. Am I missing something?
Yes, it is true.
What's wrong with this thing? It's the K point is the end of Brillouin zone.
Is there any
The dispersion
there? At
Sorry,
the
sorry?
K?
Is there?
No, it's not a gap.
There's no. Wait, it's not.
Yeah, it's
Goes this way. And you have two states there.
yeah.
At this point, it is degenerate. Essentially two states.
That condition is for non-degenerate
Yeah,
parts.
it's for
Yeah, you
non-degenerate.
have exactly
Yes,
two
yes,
states
yes,
here.
yeah.
Did you understand the derivation? It's lots of writing, but it all comes to writing the neighbors, right, taking them into account properly. So now in the exam you can solve the similar problem, something, no? Good.
So when, for example, at the K point, our alpha is 0. Alpha is the, what is it, alpha again?
I mean, just the coefficient of the T,
Okay.
which has the K dependence, which, I mean, that's why it's crucial. The whole K dependence is in alpha. And actually, I forgot to bring, as I forget things very often, they do these things as research, tie binding on graphene. I was going to bring tomorrow the papers. They take into account the first neighbors, second neighbors, they compare the band structure, they make comparison with the ab initio calculations, and actually this is surprisingly good, precise.
So at the K point, the coefficient for the jumping, the T is 0. So at that K
Sorry, what are you
point,
jumping?
the threads,
Hopping?
hopping
Oh,
curve.
sorry, hopping.
Hopping curve, because the coefficient of the hopping curve is 0. So at that point, there is no possibility of hopping.
What?
Am I right?
At the K point only.
Yeah.
Yeah,
the
K point is a very particular point. I mean, it has a different point group symmetry. Some strange things happen there due to its symmetry. So yes, the hopping is 0 at the K point. Overall hopping. I mean, the summed contribution of all the terms.
Okay.
With one neighbor it's not 0, but then summed up over all three of them it's 0. Okay, now we are finished, but if you wish we can solve the SEC tie binding as you like. I mean, I'm done, I finished the lecture. It's up to you. I can stay longer, or if you want more, I mean, just the one person of you, I mean, I can go and talk privately if you wish. The fact is we don't have many tutorials, and you will have a problem in the final. You seem to have quite some background and knowledge. Maybe you don't need these extra solving sessions, but it's up to you. You tell me what you want to do. I anyway have problems for you. I think there is one too many. two sets of problems. Can you distribute? It's a mixture of what was done previously and a few time
Just one
binding.
paper.
Yeah, you
Yeah.
get one more from there. Yeah.
I see.
Actually,
No.
You have to adjust it's a separate problem.
I'm not sure we'll have time to solve them because we'll have only 2 tutorials.
Where's the other one?
Sorry for the confusion. Everyone should have 2 sets.
You have to.
Everyone should have 2
I
sets.
have one.
It will arrive. Maybe not the most efficient way of distributing problems.
The other one.
Entropy.
Yes, I do.
Now I have
Everyone
three of
has.
them.
Putri, you
Oh,
have.
you can just keep one.
Here.
There is one more. Putri has.
Yeah, can I have one? Yeah.
So you are how many? 1, 2, 3, 4, 5, 6, 7.
Oh yeah.
I have 2 of them. And here is 2 more.
How many didn't print? Okay, I wonder how many I printed. So, in the sheet with 3 problems, the first one is a very cute problem based on the old stuff, on the free electron and that one I really enjoy. Don't look at solutions. There is no point. You can check solution, you can solve it, but try to solve it first on your own. It tests if you understood how to fill the levels, how to determine the Fermi energy, and then a little bit, I think the rest is technical. If you come to these points correct, it's just a little bit of mathematics.
So which one is the WX line?
Okay, I should draw it. Yeah. And actually this is the first on the sheet with 2 problems, where it says problems, is the one very important for time binding, for the understanding of the filling. So I would suggest you start with that one. The second one you can do from tomorrow. We still haven't done Bloch velocity. So number 2, don't try today. It's after tomorrow you can solve it. But number 1, if you have time, I would like to solve it. It's a very useful problem. Let's see, tomorrow's lecture is a little bit shorter. Maybe we can manage to solve it. So the square lattice, this is gamma, this is x, and this is w. I hope I remember well. And that one is when you solve for the constant lines, try to expand around 0, and then expand around the w point. And then there are 2 ways to solve it overall. It's not easy. If you don't look in any solution, it's not easy. But it's something that you can do. It's not terribly difficult. Okay, so you tell me now how you feel about the XCC. If you all find it easy, it's fine. If you want to solve it together, the one that Nadia gave you. Or we can say the ones who want, they stay. Those who think it's okay, it's a very easy homework. You can go drink coffee, whatever, because you have a lecture at 11.
Yeah.
Okay, so let's say who wants, he stays, and we solve on the blackboard.
I'll stop.
Sorry?
I'll stop.
Okay, good.
But I haven't tried it yet.
Okay, but somebody solved, no? You tried the FCC? You tried? This is what Nadia gave you, I think, on Tuesday.
Yeah.
And I thought of solving it last time, but the time was already up and So, volunteer. Don't feel like volunteering. Putri, you solved it? The FCC? Okay, come on, we don't have so much time so that... But this is a hard work to erase this. I'm getting tired. You can bring the notes, it's fine.
Don't we have the big eraser here in this
Or
one?
wet, we used to have a wet eraser, so it was much more efficient. I'll go wet it next time because this doesn't even erase and you have to press hard. Put it on the solid. Don't be shy here. Actually, I think it's your advantage to go to the blackboard. Because sometimes you think you understand something and you discover that something was not so clear to you, and if you're here solving it, it's likely to be... you have a problem? Or?
I didn't bring the paper.
I don't have it here, okay. You have it, Ezra?
I didn't bring the paper where I solved it.
Amel, you saw it? Come on, guys, you saw it, come. I mean, it's okay with the notes because there is no time if we cannot. You can start from the day one, but it's easier if you go from the second equation.
It's just the first neighbors.
Yes, yes. And you have to find correctly the first neighbors and FCC, which is...
So I'm just gonna use the straight.
I have to check it.
Yeah, assuming that we are only talking about the s orbital,
Yes,
and
yes.
all the other orbitals are not as important.
So imagine P here.
Yeah.
What a trouble it would be, like doubling everything.
Wait. Yeah.
So you're putting it. I'm confused a bit. Why am I writing this?
I actually.
It will be just T, no?
Sorry? No, this is not T. This is not T yet.
You will write the full equation from the beginning?
Shouldn't I? Or
I think you can just go from the solution. EK equals atomic state minus delta V, and then come to this hopping term. This is the...
EK is the, here is the atomic. And then here comes this thing. I'm gonna have to write it in a...
You also have the crystal field?
Yeah, this is the crystal field. Let's call it...
Okay.
We call it delta V.
And then the hopping.
And then the hopping.
With a bit of experience, you can just go to solving the hopping term.
And this is...
Here
I have one short notation. I'm gonna call it R. Cosine. Okay.
You already writing solution.
Sorry?
That's how you're expressing it. It's a bit different than what we did.
And then I have a special, like, different expression for what gamma R equals to.
It's correct. It's correct. It
And
actually comes, but it's not what we did in the class, so it might be confusing. You can write the sum over IKRs.
Yeah.
No? It times this the first neighbor times T.
This kind of writing is specifically
Assumes
for
the symmetry. It
cubic
assumes the symmetry.
lattices.
Yes, it assumes that the symmetry. So you're only cutting the two of them into cosine. So this is correct, but I would still prefer to write it this way, sir.
I'll just write that this thing is equal to.
So let's talk about the neighbors. You're writing the
expression of what gamma actually equals to, because it's a bit more clear.
yeah, but I'm not sure. It's a different gamma than what we have.
Okay.
I'm just trying to define the neighbors. This R. This is the R of the first neighbors. No? So
Okay.
this is okay, just not what we did in the class. So it's
so the R vectors which describe the nearest neighbors are these. I'm just not going to write the index here.
yeah.
A over 2. plus minus 1, and 0. Then we'll have a second set.
Group.
Yeah,
So this is 4 neighbors here, all combinations of signs.
Then I have plus minus 1, 0, plus minus 1, 0, and then I have a third set, which is a over 2, 0, plus minus 1, and plus minus 1.
Yes, yes.
So it's just hard to imagine. Yeah, it's like this vector down there, this vector down there, and then
It's
another.
the plane.
Yeah.
In this plane there are 4
Yeah,
neighbors.
yeah.
In this 4 and then in this 4.
And this way, if we just sum up all these integrals, I mean the
Yes.
exponents, we get.
So it's lots of writing essentially. You understand, no? It's, you have to put all of these into exponent here. And you'll get many the same with opposite sign.
And now
So you have many cosines. You get 6 cosines.
Right.
You get
it is minus, if I'm not messing up, it's minus t cosine 1 over 2 kxa times cosine 1 over 2 ky.
okay. So you have 6 cosines
Yeah.
sum,
and just
and
combine
then,
it.
and then you can actually rewrite it in this form.
Cosine 1 over a ky a cosine 1 over kza, and then I'll have kx kz term, which will be 1 over kx a cosine 1 over kz a. I have x y y z. Let's do it this way, z and x, and yeah, I think the coefficient is correct.
Yeah, I think so. So actually, what you are getting here, you will get cosine kx plus ky over 2, plus cosine kx plus kz over 2, which can be also written in this way. Now I hope it's correct because I'm not.
This is correct. I'm not quite sure about,
I mean, this
because I wrote it in different.
It's
different
40.
it's 40, yeah, because
And
it's
it's
yeah.
important because you
Yeah,
won't
yeah.
get the right thing.
Oh yeah, 4. Why did
I
I?
mean, if we're going to plot it anyway,
Okay. And
We're
now
just
you want to
assuming.
plot it along which direction does it say?
at
Gamma.
x.
Gamma x.
So the Brillouin zone is a cube. The gamma x point can be, for example, we'll take it for kz equals to 0. So I'm just going to erase all the kz terms. I have this not contributing anything because kz is 0.
Well, I don't have to erase.
You need it for the
Okay, okay.
I mean, let's not give it.
Exclamation points.
K
And
1 over 2 kza. This term will give me 0. This term will give me 0 because I have kz's there.
2 pi over 8 and the energy. Okay, so from 0 to 2 pi over 8.
This is gamma x, right?
Yes.
yes.
Yeah. So if we are on gamma x, it means that the kx and ky are the same. This is the gamma x, right?
Ky is 0.
This is gamma and
A.
this is x.
No,
This is
along
x.
A.
Yeah. So it means that
Ky
ky is 0. So this is just
One.
1, and we're just plotting for t times this thing.
But be careful, this is not 0.
We took kz as 0.
Yes, the cosine of 0 is 1.
Ah, yeah. So yeah, it's E atomic minus.
But one can make many mistakes, silly mistakes. The things you know, you just, I mean, as you saw me also getting confused. So it's important to go through problems to practice a bit and not to get confused with something. It's very easy. I mean, this is a common mistake in the exam that people take cosine of 0 to be 0.
I'm just gonna write it still.
I know.
Yeah, it's 1 over 2 ky, which is 1,
Which is 1, yes, with 0.
I have this also equal to 1.
So plus 1.
So this is plus 1, and I have 1 and like 2 to make it 8, and I'll have this thing.
Okay.
Yeah.
Yes. Yes.
So now
You all follow? He didn't want to write 2 here and 2 here,
Yeah,
so it's
it's
okay.
just 8. So if kx is equal to 0, then
Yes.
this term is 2, and we have like
I mean, is it correct?
Yeah, it's 2
Yeah,
and 16.
It is.
Okay.
it's minus 16t. So
Okay.
how should I like?
You write it.
No, I mean
You write it as I mean the whole thing.
yeah. Okay.
EA
This
minus.
will be EA minus delta V minus 16t. And if we take kx equal to 2 pi over a, then we have here cosine 1 over 2 pi over a. These things cancel out with a minus 1 and it's 0. So
Yeah.
it has
It's
to go.
cosine.
It has to go something
Yes.
like this.
Yes. Yes.
Something like this.
Yeah. Okay. It's. Yeah. Just don't draw straight line in the exam.
Yeah.
Because that happened too, and you cannot give a point for that. I mean, at least it should look a bit like cosine. And what is the bandwidth?
The bandwidth is just twice of this.
Right, twice?
It's just
This.
this, yeah. Not
Yeah.
twice. There's
So this line here is EA minus delta V.
yeah.
So it is 16t.
16.
So the bandwidth is 16t. Okay, did you follow? I mean, we cut a bit here, but if you do the exercise, you will get these nice terms of cosine kx plus ky over 2a and so on. It's quite some writing. So please do it. This is a basic exercise. If you're unsure before going to more difficult problems, you can do simple cubic or BCC, whatever. If you I think there is a class here. Thank you.
There's a really bad problem with my laptop. When I close it, it doesn't shut down. So it was running all the time in the bed and it was so heated up.